Okay, so welcome to the second lecture of introductory chemistry in a more advanced approach perspective to this. So this is lecture 2. This is fundamentals, atoms and elements. So after we're done with this lecture, I will upload a PDF of a problem set that can accompany this lecture. You guys should be like, if you want to try it out, you can try it out, and I'll make a video to the solutions later on. So we're gonna have the link to the problem set corresponding to lectures 1 and 2, and we're gonna have the blank notes in case you guys want to follow along. I'm gonna also try and put a PDF in the description to the notes so you guys can follow along. So let's get started. So matter can be broken down into elements. So yeah, that's basically it. So elements are fundamental units of matter. So let's go ahead and look at an example. This is CO2, carbon dioxide is matter, so you can exhale it and you can also feel it. So let's draw the structure for CO2. So right here we have carbon dioxide, which is CO2, and it has a bond angle of 180 degrees. And so this is what we would call linear. So remember that oxygen is more electronegative than the H's in H2O. Remember that from last lecture. Oxygen here is also more electronegative than C. And going back to last lecture, remember how we drew our arrows like this for water? We're gonna draw them like this for for carbon dioxide. To show that electron density is going towards oxygen. So I'm not really going to test on electronegativity and electron density just yet, but just for your information. So the geometry is linear, as we said here. Remember, it was not linear in last lecture, it was bent. But in this case, it's linear, because we have, basically we just have 2 bonds on each side instead of 1, and 2 bonds typically correspond to linear geometry. Like that, right? Ignore that. I don't know what happened there. Like that. So these 2 carbon atoms can be bonded to anything else on either side. But right here we have a double bond that would correspond to a linear geometry. And you'll learn more about that probably in organic chemistry. So yeah, let's continue. So right here we have 3 atoms, which is 1 carbon and 2 oxygens. And at the same time we have only 2 elements, which they are carbon and oxygen. So 2 types of elements, but 3 total atoms. That is what we have. So carbon and oxygen are the fundamental building blocks of carbon dioxide, right? According to what we said about elements being the fundamental units of matter. And they're also the fundamental units of molecules, which molecules make up matter. So notice that there are 2 bonding lines connecting each oxygen to carbon, like I said before. This is because the atom carbon likes to make 4 bonds, and oxygen likes to make 2 bonds typically. So you'll see more about that later when you get to like Lewis structures and stuff like that. So I guess we can continue now. So let's look at elements present in the human body, and let's write them down. So we're gonna have oxygen, which by mass will be most abundant in the human body. So it's most abundant, and that means there's like more of it per mass. Most abundant by mass. You'll notice that a lot of organic structures, a lot of amino acids, all this stuff has oxygen in it. So we'll look at that. You'll see that later on. So this is carbon. And this sign just means that there is more of oxygen than carbon, and there is more carbon than hydrogen. And there is more nitrogen. Sorry about that. So there's more nitrogen than trace elements. So these are actually small amounts of elements, like really small, smaller than nitrogen, like in terms of percent mass, small amounts. Oh, just a second. Right, so that's small amounts, like carbon. Like calcium, sorry. Calcium is just an example, but there's like a plethora of trace elements which we won't talk about today. It's not that important. So you can look it up on your own. So yeah, that's calcium. So calcium's in your body, but it's in smaller amounts than nitrogen is in your body in terms of mass. So as we can see here, oxygen, carbon, hydrogen, nitrogen are important elements present in biological and organic molecules. So you'll see a bunch of these in organic and biochemistry as you guys go along in far beyond introductory chemistry. So this is an example, which is an amino acid, glycine. Glycine is a type of amino acid. So let's go ahead and draw the structure for this compound, this molecule. So you have an oxygen bonded to a carbon, and we have a oxygen bonded to a hydrogen group here, which we'll call a hydroxy group. You need to know that. This is a carbon. This carbon is bonded to an H2 group, which we call an amino group. And yeah, we'll see that later on. Yeah, and it's bonded to 2 hydrogens. So remember, carbon likes to make 4 bonds, and look at all these carbons. They're all making 4 bonds. So this is what you would call glycine. And let's go ahead and look at the structure. You guys will see more in organic chemistry. This will be an H, and this is more like the line structure you'll see in organic chemistry, the organic structure. Each bending in the line represents a carbon. So these are the same. They're the same molecule, they're just drawn differently. So this is the organic structure. I want this in red. So these are same. And that is your organic structure. And I want you to look at the elements here. So yeah, like I said, they are the same. They're just written differently. And amino acids are the building blocks of proteins, right? Much like elements are the building blocks of molecules, which make up matter. So this is a good example of what a building block is, and how you guys can picture help picture how an element is the building block of a molecule, and how an amino acid is the building block of a protein. So this is a good way to like picture it, and you'll see more of this in like, you'll see amino acids more in like biochemistry, and sometimes even organic chemistry. Like you can see it in there, depending on what your instructor covers. Some instructors don't cover amino acids, some do. And yeah, like as we can see, like I said, look at the elements. We have carbon, we have oxygen. Well, these are the different types of elements, right? We have carbon, we have oxygen. What else do we have? We have hydrogen, and we have nitrogen. And there's a good example of these elements. A good example, right? It all contains these ones, the ones we described. So that's a good example of a biological molecule, and that has those abundant elements in your human body. And amino acids they make up proteins, and amino acids are in your body, so it makes sense, right? So yeah, so carbon, oxygen, hydrogen, nitrogen, how I circled in red here for the amino acid, for glycine, are the building blocks of glycine. And notice that, like I said before, carbon, oxygen, hydrogen, nitrogen are elements, right? So I guess we can continue some more. So what is an element? So let's look at some examples. So let's look at the example of a gold bar. So we're going to assume that this gold bar is made of 100% gold, of 100% pure gold, versus a gold atom. So we should draw a representation. Sorry. We should draw a representation. So this is your gold bar. And this is your gold atom. We can just draw it as a circle. This is your gold. AU is just the elemental lettering, whatever that's called, your elemental symbol for gold. So these here are both elements. I'll draw it in red. So they're both elements. So gold here contains a large amount of individual gold atoms. Like the gold bar contains a large amount of individual gold atoms. And the gold atom is the smallest representation of the element. So in simplest terms, an atom is the smallest representation of an element. So it is still that element, but it's in its smallest form. So let's say, like, think about it this way. If I have a gold atom, is it still gold? Are its properties, are its physical and chemical properties still that of gold? The answer is yes, right? Now, if I have if I have trillions upon trillions of gold atoms, forming a gold bar, so they're all together forming a gold bar, would that still be gold? Would it still have the same chemical and physical properties as the gold atom? And the answer should be yes. So that is how you should think about elements, right? An atom versus an element. So an atom is just the most basic, smallest fun representation of what an element is. And the element can be the atom, but it also can be like a whole collection of those atoms to make a gold bar. And so let's write that down. So the gold bar is a macroscopic, meaning large, macroscopic form of gold element, right? Of the element. And then atom is the smallest form of the element. So this is another example for you. This is molecular oxygen, O2, versus elemental oxygen. So let's draw molecular oxygen. Remember, oxygen likes to make two bonds. And this is your oxygen atom. That's just a circle with an O in it. That's your oxygen atom. And these two are both elements. This is your O2 molecule. And this is your oxygen atom. So a molecule, which we'll talk more about, not here but later, is two or more bonded atoms and can be the same element, as we see here with molecular oxygen, can be the same element. But they can also be different ones, but you'll see that later on. So yeah, remember that oxygen prefers to make two bonds, like I said before, as displayed by our molecular oxygen. So both of these are elements, right? They have the same atom. So oxygen, O2, molecular oxygen, is just two oxygens bonded to each other. Hence, it is a molecule, but it is still like an element, right? It's the same type of atom. So remember that. So we can have molecular elements such as O2, I2, stuff like that, and we can also have just an individual atom that can be an element. So this is a good representation of molecular element. It is still an element, but it is a molecule because it is two atoms bonded together. And like we said before, an atom is the smallest representation of an element. So in this case, the oxygen atom is an element. And yeah, that's it. That's a good example. Again, you have questions, you want me to make things clear, just let me know. And this is that an element cannot be broken down any further. So remember that an atom is the simplest form of an element. Like I said before, I said many times here before, if we can break down that atom into its subatomic particles, like your neutrons, your gluons, stuff like that, neutrons, electrons, protons, stuff like that. Gluons is more like other more advanced stuff, so not for here. So we can break that down into subatomic particles. We can lose the properties, we'll lose the properties and identity of that element. In other words, it is not the same element anymore, and it's not the same atom anymore, right? You've broken down the proton, it's not going to be the same atom. Chop that thing in half, it's not going to be the same atom. And it's not going to be the same element. It's not going to have the same chemical and physical properties. So that is what I want you to take away from here, from today's lecture. And again, if you want a copy of the notes, of the blank notes, so you can follow along, I'll link that in the description. And there's also a problem set if you want to try that out. It corresponds to lectures 1 and 2, which you can find in my Introductory Chemistry and Advanced Perspective playlist. You can watch those lectures and see if you can attempt some of the questions, and I'll post the solutions to the questions in a later video. So yeah, that's it, and good luck and thank you.